Start the recording. Okay, so what we will do now is to move on to what's called broadband arrays. So we have really focused so far on arrays that are typically lambda over 2 spacing. We've seen what happens when we change the spacing. We've seen some of the cost of changing the spacing in an array, for example, grating lobes and so on. So now we should understand what actually happens when we have to design antennas which are broadband. And when you design an antenna that is broadband, you have to ask, what is half a wavelength? It's not trivial to say anymore what half a wavelength is, because if you have a huge frequency band, which frequency should you pick, or which wavelength should you pick to call it half a wavelength? So let's look at one case here that we say you would like to design an array with more than 100% fractional bandwidth. And the fractional bandwidth that you know is the relative quotient between the higher frequency minus the lower frequency, so the bandwidth divided by the center frequency. And now it can sound like 100% bandwidth would be infinite bandwidth, but that's actually 200% bandwidth. So the bandwidth of 100% is not everything. It can go to 200% in the case of bandwidth. And an application for this is broadband arrays. You can see one here. You can see a large array antenna. You can see many elements. And this is actually a broadband array. And the main application so far for this broadband arrays has been, again, military applications. But of course, it's coming also again in communication setting, because imagine now the base station scenario. You put huge arrays there. And if you have now the large arrays, you should cover, of course, all the frequency bands. And you cannot make one antenna array for 700 megahertz, another one for 900 megahertz, and then from 1800, 1900, 2.35. Maybe you could cover all of those in the same array. Then you would like to have actually one array element that deals with them all in some ways, which can be a huge advantage in many cases. But when we do that, we really have to ask, how do we design it and what comes in? And when I talked about mutual coupling before, these are antennas that are designed with mutual coupling, because a mutual coupling can become so large here, so you cannot neglect it. It's really incredibly important parameters, and you can gain on having mutual coupling, but you have to design it correctly. So if we take one of these again here, we can see what the design requirements are. And for an array here with a typical application like radar application, communication application, there is a strict requirements that you cannot really have grating lobes. And the grating lobes usually creates a huge amount of problems for these ones. And this is especially for the phased array type. And that is that the impedance, they cannot be matched over this range of grating lobes. And then, of course, if you have grating lobes, then you cannot stereo beam in only one direction. You always get multiple directions. And you don't want to have that. If you have a phased array, you want to shoot your beam in this direction, not this direction and that direction. Imagine you receive a signal, you don't know if it comes from there or comes from there. Where is your enemy, for example? So you cannot really have grating lobes. That is a requirement. And that means that the distance here typically has to be below half a wavelength, or at least below a wavelength. It depends a little bit on what scan angle you are looking at and what element patterns you have. But it is in the range of half to 1 wavelength. That is where the spacing sits. And now, of course, if you have many wavelengths, it is the worst one that really matters, which means the shortest wavelengths, which is the highest frequency. So the highest frequency controls the element spacing. And that means that all lower frequencies will be much closer together than half a wavelength. They will be very close together, which means that the mutual coupling will be very high for those elements. And that comes in the design and thinking in all of these cases with broadband arrays. So if we look at an example, let's say that you would like to make a broadband array. And now we pick here some frequencies. So we say that the lower frequency here is 4 gigahertz. and I take the higher frequency, 12 gigahertz. So some application for that. So now you have a bandwidth in that cases, which goes from 4 to 12, which is 8 gigahertz. You have a center frequency again here, which is 8 gigahertz, which means that your fractional bandwidth in these cases is 100%. So B is equal to 1, which is 100% bandwidth. And the grating lobe in these cases comes from the requirement in these cases, N5 requirement in these cases would then say lambda over 2. And that is then the highest frequency, so the shortest wavelength, which means that the spacing in these cases has to be below 13 millimeters. That is the spacing I can have in these ones, which would mean in these elements that sits there, the distance between two tops in some ways. That will be maximum 13 millimeter in this case. If you go for your longest wavelengths, which is your shortest frequency, then the wavelengths here is 75 millimeters. So that means that the elements there is really like fifth of a wavelength in spacing, which is incredibly tight together. They're really sitting next to each other, those elements, because the spacing is fixed. You just control the wavelength you transmit. So we have to think something is happening here. And what is happening here is that we cannot really treat this as we did before with an element pattern and array factor, multiply them. We have to think about this as one. They are an array. They are not an element put in an array. It's an antenna array from the beginning. That's how we have to deal with this. So let's see now what could happen in these cases. So if we do, for example, a lambda over 2 spaced array again, so we take this typical case. If we look at patches here, so they would then have a size, so the length of these patches here, which is approximately lambda over 2, but it's lambda in the substrate. So it's shorter than a free space lambda. And if we now have a lambda here of this size, so you can see the length of lambda, yeah, then this one here would be half a lambda. So that is the spacing there. And the elements are smaller, so they fit in this kind of scenario. This is a patch array. It's a really good array in some ways, but it only works for a very narrow band of frequencies. But your patch is narrow band, so it's no problem. It works for what it should. You can do the same thing with, or if you look at the currents of these ones, what's happening in these cases, just a second. What's happening in these cases is, of course, that you have currents on each element here, and you have the dominant currents in some ways on the edges, and then it goes to 0. And then you have some other small currents, and they fit in the sampling of this lambda that you would like to send in some ways. They have similar sizes there, which means that it works together. Okay, there was a question from someone raised their hand.
Yes, from
Yeah.
sorry, here the distance between the horizontal distance between the patches are not equal the vertical distance between them, correct?
I think in this case I've been drawing, they are the same here. So
okay,
you can make it different. You can have different, like you can have a different sampling there, and you can have a different there. Those doesn't have to be the same. There is no requirement to make these the same. I think in the one I've been drawing here, probably I've been drawing that with the same, but it's not a requirement. And of course, this doesn't have to be exactly lambda over 2. It works with having lambda over 3 or 0.6 lambda, but in the order of lambda over 2. That's what you need.
Yes, but the distance here should be in vertical or in horizontal side.
I think in the one I've been drawing, it's the same. And to make it really lambda over 2, it will be the same. So this would be what's called a linearly polarized array, and it's here lambda over 2. But you don't have to have the same in these cases in, let's say, this distance here, I can call this dx, and I can call this dy. They don't have to be the same. But if you say a lambda over 2 array, they are the same. So both of them here would be the same. But there's no sharp requirements on it. But they would be approximately the same. If you start separating them, so you make one like 2 lambda spacing, you will get grating lobe in one of the cuts in some ways, one of the directions. Because you can control in some ways with the spacing in one, you can call like this direction, and the other one control this one. And you need both of them to be below lambda or below lambda over 2 to avoid grating loss. And the spacing is, you can take any points. You can take the spacing, for example, between the feed point here. It doesn't matter which point you take. That is the spacing between these arrays. So it's not edge to edge of the patches. It's like the center of the patch to the center of the patch. That is the distance as it's there. So if you think, it's not like this distance. Or let's see here if I draw it. It's not this. This is not the distance. That is the physical distance between the patches. But in the array, it is, you can think more the center of the patch to the center of the patch. That is a separation between. Okay, so here is of course where the currents looks like, and the current between here is 0. So there is no current between these patches. But it fits the sampling now of lambda or lambda 2. You can do the same with the dipole. So now again, I have the just dipole elements instead. And again, of course, this is now a spacing and this is a spacing. And here both of them are lambda over 2. But they are physically close, of course, here. They're almost sitting together, but there is a separation between them in these cases. And if we do the same here, we can look at the currents looks, because the current gives the radiation. So it means you have strong currents here, and in between here, it's equal to 0. So in the gap there is no current. So you have current, no current, current, no current, no, and so on. But it fits again the sampling of lambda. Because it in some ways, it's very strong, it's weak on the order of lambda or lambda over 2. So it fits this range in some ways. So the elements here really fits in this lambda over 2. But now if we want to go for this broadband arrays, so that means that of course I need all wavelengths here between, let's say, the highest frequency, shortest wavelengths, up to the the lowest frequency, which is the longest wavelengths. And the spacing is now determined here by lambda for the highest frequency. That is the shortest wavelengths you have. And that means that if you would like to do that, you have to pack here in some ways a separation distance, which is between these two. That is lambda high over 2 in that case. And that means that, of course, at the lower frequencies, the spacing is very short. I mean, it's the same physical distance, but different electrical distance. And you need to put elements in there which are incredibly broadband. So you have to pack really small broadband elements in some ways. And you can try to do it. It's a recipe to disaster. It doesn't work. People can try. So in case here, we have to ask if there is something better to do. And what is better in this case is to live on the mutual coupling. So instead of saying that you do an element and you do an array factor and you combine them, you say you do a broadband array. A broadband array has mutual coupling. Don't neglect it, embrace it. So use it instead. Then we actually can decide better broadband arrays. But it means that our philosophy have to change for this kind of arrays. So if we then look at these once again, we can see now our lambda over 2 dipole array. And as you can see again, of course, the current here has a certain shape, but it's like the same as the wavelengths in some ways. They are of the same order when I have a lambda over 2 spaced dipole. But now assume that I have a broadband array. So at then the longest wavelengths, assume that my wavelengths looks like this. Now I have a lambda over 14 dipole array, which means that this distance here is not now lambda over 2. The length of this dipole is approximately lambda over 14 or something. So very, very short. And still here, if you think about it, the current has to be peak in the middle where you feed it, triangular shape. It has to be 0 at the edges because the antenna element stops there. And then the next one have to pull up, and it has to pull up, and so on. So the current here is really strong current, no current, strong current, no current, strong current, no current. And you would like to have something that looks very different. You would like to have a current here instead that has in some ways kind of this shape. So you don't want it to go to 0 between these ones. You don't want the current to disappear between the elements. And then you can ask the question, how can I do this? How can I create an element where there is a strong current between them? And you can do that with either something that's called capacitively coupled arrays or connected arrays. So the first one, skip the separation between them. Then there is no requirement that this current goes to 0. And it can be done as I draw here with actually having the metal into each other. You have to fix a lot of things with it. You can also do it by having your dipole element coming out here, and then you in some ways make a big capacitor here. So you have two elements here which fits together like in fingers like this. You make a finger capacitor. So they are not touching each other, but at a higher frequency it's capacitive, and the capacitor then actually goes to a short circuit, and it looks electrically that they are connected. And that means that you can actually have a current on these elements that start looking at the half a wavelengths you have. And this is the philosophy to get broadband arrays. And now we can ask the question here, is there an element in this? Is there an array factor? And actually, no, it's not. It's just a broadband array. And it has to be designed together with its neighbors. So you have to care about your neighbors when you design these elements to make them work well. And that is how you do a broadband array. These capacitively coupled dipoles is one of the best you can do. You can make incredible bandwidth over large arrays for it. Another version of seeing the same thing is to look at self-complementary structures. We will come back to that a little bit later when we actually talk about broadband antenna elements. And a self-complementary array is something that if you change what is air here and metal, so PEC, and you interchange those two, you get the same structure. So think about the checkerboard. You have white, you have black. And of course, they are the same. If you change all the white one to black and all the black one to white, you still have a checkerboard. There is no difference there. And that is a structure here where I can just change this. I get the same. And now assume here that I feed it in the center. So these black dots here are the feed points. This is a self-complementary structure which actually have incredible properties. A way to analyze these ones is that you break it down to unit cells. So if I take this and I study these antenna elements and I do it only over this piece here, then I use periodicity and I say that the next one here actually looks exactly the same. So all of these elements here look the same. And now what I have to do is that all the feeds has to have only an amplitude and a phase, and the phase has to be smoothly over the region here. So in some ways, direction of radiation in one direction. Then all of these are the same, which means I can study only one unit cell of this. It's periodic. And in this case, you can actually make a smaller periodic structure. And this is what you would put into FECO to simulate this one. Very, very small structure, very easy and quick to simulate. The good thing with these ones is that it actually have a frequency independent input impedance. So the input impedance of this one is half of the free space. So now you can ask the question, what is the bandwidth? In theory, unlimited. So by doing this, you can get an incredible bandwidth. And again, you can see the elements are strongly coupled here. This is like one element here. It goes between two feet. They're basically sitting together. And that's what's happening in many of these cases when you want this incredible bandwidth. And these self-complementary structures are actually prototypes of many broadband antenna elements, both arrays and elements. A structure that has this feature is actually a way to make something broadband. And if you remember from the course, an antenna we looked at before was the spiral antenna. And the spiral antenna is almost self-complementary. You can think about the spiral going out there. And if you just change what the spacing is between those wires and you change it with the wire, you basically get spiral again. So it has these properties. A bad thing is that you can ask, how big is this one? And unfortunately, it's really big. So that is the bottom side of it. Of course, it has to be infinite in size to really work. But that means a finite one is a good approximation. And in reality, if you make this type of checkerboard antenna, it can have very large bandwidth. It will be created here the lambda for the lowest frequency has to do with the size of these ones, the total size of this array. And the higher frequency has to do with the modeling around one of those feeds. In a similar way as you think about the spiral antenna, where the circumference about the spiral was the, in some ways, longest wavelength you can fit, and the feed gave the highest one. A practical problem again is feeding. If you think about a spiral antenna, what was a spiral antenna? You need to attach it to a surface. You have a ground plane, which means that that limits the bandwidth. But it's a good prototype for many cases. That's one way of actually getting out of these cases. So the mutual coupling here is in some ways very high in broadband arrays. We cannot neglect it. It is high. And you design them actually as infinite arrays in typical cases. So you use this periodicity, and then you say in reality, it's a finite version of that one, which means simulations can be done over what's called a unit cell, so small structure here. You can simulate all of the antenna. And that means that you include mutual coupling directly in your simulations. So you live on mutual coupling in that case. If you look at parameters, they will depend on the scan angle. So if you have a reflection coefficient or impedance, it's depending on how you scan the antenna elements. And then the last thing is that, of course, edge elements here are different. So if you think about these elements here, they are very different from an elements in the center, because the element in the center has a lot of neighbors. The elements on the edges here has no neighbor on one side, which means its impedance will change a lot. And in reality, it means that you take actually the array here, and what sits around it here on the edges are dummy elements. They are the same, but they're actually not fed. There's no electronics to these edge elements, because you want the inner elements to see the same environment. All antennas should see the same environment. And that means you need to cover it with dummy elements around it. So you have some special treatment for these edge elements. And one case we can see with this, there are many versions. The previous picture was called Vivaldi elements. You can do other ones. You can have some dipole type elements. You can have some structures here with some called mushroom elements and so on. And they can actually make these antennas very, very broadband. And it can be shown in these cases that the bandwidth here, so the total bandwidth in lambda, so the fractional bandwidth B times the center wavelengths of this, is approximately or limited by 17 times the thickness. And you can get very close to this with actually real designs of these ones. So there is a good rule of thumb how far you can go, and actually it's a limit you cannot really beat. The only thing you can do is, of course, to have a different matching. You can add magnetic materials. In practice, it's very hard with magnetic materials. And you can actually go down there to something that is ridiculously bandwidth on a very, very thin structure. And in many cases, you can design close to it. So we know good things that can be done for these cases. So that was actually everything in this course about arrays. So now we are down here. So before I move over to the next part, which is a little bit talk about this method of moments, which is this numerical method, any questions about these array designs or arrays in general? Otherwise, we will move on. So I will stop sharing that, and I will just change the document. So then we continue a little bit about different computational techniques, which is what you have been using inside of your simulation software, so FECO. It is a way to actually solve general electromagnetic, problems, and particularly antennas, but also scattering problems, RCS of a structure, and so on. You can simulate almost anything. And we have focused on a method here that's called method of moments. I will describe what that is, but there are other types of solvers that can be good in other cases. And generally, this is something that's called this computational electromagnetic. So it's a topic here that you should have an idea what it is, because that is actually what you use in these simulations, of course. So let's see what actually is happening for these cases. I'll just wait, I'll just change this. And this one here. Yes. So let's look at a few cases of this, actually, what we can compute in some ways. So in the solver that you have in FECO, in these cases, you can choose quite a few different solvers. So in these cases, you have what to say here, a time domain solver. So that is the one that is used in many applications down by very complicated antennas. You put biological tissues and so on, and there you solve the structure in the time domain. It is one of the solvers. And what actually exists in your case here with, let's see here. For some reason, I don't get my drawing up. I don't know why. Let's go back here. Okay, never mind. So this is a solver that we can choose, and in FECO they have a lot of different solvers. Like you can see here, you have some general settings. Here we have an FTTD and finite element software, FTTD settings, and so on. Finite element method is another version of solving this, and what we've been doing in the course is mainly this integral equation solver, also called method of moments. Then there are what's called high frequency solvers. So for different problems, you have different solvers. And of course, to really be able to solve something well, you need to have some idea what's happening in these solvers and which solver to choose in these cases. What's happening in basically all of these ones is that you take your structure and you, in some ways, discretize it to a finite structure. So one thing here is, for example, in these cases with these dipoles that we see down here, you can see a lot of small triangles. And what that means that in reality, you have your dipole, it's like a piece of metal that sits here. You approximate that one, that the currents can only change over a certain scale. And if you have very few triangles, it's like the sample of the field. You can maybe not describe the currents you should have there. And put more of these triangles, you get a finer sampling of this current. So you always need to have sufficiently many sample points to be able to describe what is happening with your currents. And that's done with something called a mesh. And the one you've been running in your patch antenna and also the cases for a lot of other structures have typically been a surface mesh. It can also be wire mesh. Both of them exist. And in those cases, each of these triangles is like 1 degree of freedom for your current. If you instead were solving the same thing here, but you do it in the time domain setting, so for example in FTTD or the finite element method, then you actually discretize the entire space around your structure. So that means that you take your, in this case, a Yagi-Uda antenna with 3 dipoles next to each other here, and you embed it into a huge volume. And then you discretize not the current on your structure, you discretize the electromagnetic field outside of your antenna. But it's the same thing. It's like one, you discretize the current, and one, you discretize the field, but you still discretize it. And then you solve the equations for Maxwell's equations for these cases. And when we do it on the surface, we have to use what's called integral equation solvers. And here we do partial differential equation solvers. So Maxwell's equation is written as a partial differential equation. But in all of those, discretization is important. And you need to have a fine enough discretization to make your results stable. So a good way of checking it is to simulate it on one mesh, then re-simulate it on a slightly finer mesh, and see that your results do not change. Then you can, in general, trust your results. So when we look at this time domain solver, so the FTTD and the finite element methods, it computes electric and magnetic fields in a volume surrounding the antenna. So if you have here your dipole, you feed it here. This is the metal structure, but you actually discretize everything around these ones. And that means that you have some box around that is discretized. In FTTD, it's typically straight lines. In the finite elements, it's more these triangular shapes that sits there, tetrahedrons in general in a volume. One of the painful things to do this in the time domain is that, of course, the electric field don't stop here at the boundary. So then you add some absorbing boundary conditions around it. So you put it in a wall that absorbs the wave that comes around it. Very similar to what you will do next week when you measure your patch antenna. You will go to an anechoic chamber where the walls are filled with absorbers. And here we have to do the same numerically in some ways. And you have different mesh cells that you can use. In FDTD, you do time stepping, so you start solving Maxwell's equation at time 0, you move up in time. And you actually take each time step and you solve them and you move on in time. In finite element method, you do it at a single frequency, and then you solve a huge linear equation of Maxwell's equations in some ways. Discretized version of Maxwell's equation, and you solve a huge matrix equation. And that you can typically do iteratively in these cases. When we do the one you have been using, which is this method of moments, there we instead start by, let's say, only meshing the geometry. So if you have this PEC geometry, so you have your structure, which is a good conductor in this case, you approximate the structure here with your triangular mesh. Many cases you would like to have fine elements here around the feed because the currents can change quite roughly there, and maybe slightly more coarse when you sit outside of it. This is from a program called CST, which is similar to FECO. It's another solver. And the discretization here means that your current that you have, or current density, is written in some basis function which are known times some coefficients. And you only try to determine those coefficients. And this is where you can see this as a sampling problem. Your current change over a certain shape, you need to sample it fine enough to be able to describe it. So you need the convergence in this case. And when you have solved the method of moments equation, you get out the current density on your structure from these cases. So again, you have to solve a huge matrix equation for these cases, and you can get out the current. And then when you have the current given, you can determine circuit parameters, because if you know the current, you knew the voltage, you can take the quotient, you get the input impedance. If you have the input impedance, you can determine the S parameters or reflection coefficients. If you have the current given, you can take the Fourier transform of it, and you can compute the radiation properties. And this is the part that we've been doing in the course. So you can compute this radiation vector, which is basically what this software is doing. So the same integral that you are solving here, this Fourier transform type integral with its phase factor, that is done in the software. So they are computing the same thing you've been doing there. And that gives off this radiation vector, and from the radiation vector you can get the radiation pattern, you can get the radiation intensity, and you get how this one radiates. So that is done inside of this, inside of the software. And if we think about a cost for this, of course, here comes a trade-off for what is good and bad. When you do it in this method of moments, what you need to do is to, in some ways, have your triangles that you need to discretize. So you need to divide it into a certain number of unknowns here. So if you say I take each wire here and I discretize it into 50 triangles, I approximately have 3 of those, so I have 150 unknowns. Or yeah, 150 mesh cells in these cases. And the unknowns of this is then higher because I need to have each basis function that can live on them, which is more than the number of triangles. So I probably get around 3 times that one. And that's because in a general structure on each triangle, there live typically more unknowns, because all the unknowns lives on the edges of these triangles. And then I have some matrix elements, which is the square of these ones. And then I have to invert it. That is the cost I have. If I do the same with the finite element method, then I discretize a cube. So here I will have a huge amount of unknowns. So instead of 450, I have like 6 million unknowns. But the number of matrix elements is not so much worse, and actually solving it can be as fast. So a little bit comes into the structure of the solutions in these cases. But in general, this method that we've been using, this integral equation that you use in finite elements, it's very good for structures with currents on a few wires or surfaces. So typical antennas where you have, for example, a Yagi-Uda antenna here, there's only current here, here, here. There's no other currents. It makes very few unknowns. In your case with the patch, you have currents on the top of the patch, and actually the dielectric can be taken care of analytically. and that doesn't add number of unknowns, at least for an infinite dielectric. For a finite one, you will have to add it. If you do it with a finite element method, you have to put a box around your structure and solve Maxwell's equations on that box. So slight difference in some ways, what is good and what is bad in these cases. So again, if we see finite elements, of course, we have this structure, we discretize everything, and then inside of that is this discretized again antenna structure. So we have to discretize space, and the discretizing space gives the the electromagnetic fields, and from the magnetic and electromagnetic fields, we can actually compute the currents on the structure as a post-processing step. So in general here, it's very difficult to say which numerical method is best. It really requires kind of a lot of deeper knowledge in what's happening there. If possible, it's often good to use more than one method to compare the results. Like in FECO, you can solve it, for example, with the integral solver, but you can also solve it with a finite element solver. And if you give the same results, you're typically happy. If they give different results, maybe something is wrong. It's in most cases very important to refine the mesh to investigate mesh convergence. So if we think in reality, there is no mesh. This is continuous everywhere. And that is the result we would like to have. And then we have to have the assumption there is that if we sample it finer and finer, the results converge. And that is the result we would like to have. So when you have done one simulation, you got the results, it's good to change the mesh and see that you have the same result. Then you can trust your results much more. And if you solve it 2 times and the result differ, the only thing you know is that at least one solution is erroneous, maybe both. That you cannot know. Then you have to refine it one more time and see what happens. So you have to check the stability of these solutions when you actually change the mesh, the mesh, because your solution should be independent of the mesh in these cases. So if we see what we get out in these cases from this method of moments and the current distributions, what's happening inside of it is that we need to compute the current distribution. If you think about the course, we really learned how do we determine the radiated field from the current, but not how we determine the current. And that is the key part to really determine in these cases. So what we need to do in these cases is that we really need to get back in some ways how we can determine the current. And we have learned some analytic expression for small elements, Hertzian dipoles. And that's almost what's used in this software. And we made some assumptions of the current distribution on, for example, half-wave dipole and patch antennas, which works in many cases. But if we don't have these good assumptions, we need to compute the current density. We need to compute the shape of it. And the strategy to do it is to decompose the current density here into many small parts. And each small part is almost a Hertzian dipole. It's not exactly the same, but it's almost the same that we've done in the course. So each little unknown is almost like one Hertzian dipole that sits there and radiates, and we should just determine the amplitude and phase of that Hertzian dipole. That is the unknown, which means that you will have many unknowns because they will fit many small dipoles on your larger antenna structure. And this is your meshing. Each mesh cell, you could think about one Hertzian dipole. In reality, it actually sits one on each edge, but it's not really Hertzian dipole. You actually simulated more accurate than that. And then you can determine the radiated field from each small part. And you get an equation by adding up that the electric field is 0 on the structure. That gives you one equation, because you know that the tangential component of the electric field has to vanish on the metallic structure. That is the boundary condition for a perfect electron conductor. And that is the boundary condition that let us determine the current. So what we do is that we take our structure, we use these small dipoles here, so almost a Hertzian dipole, and we say here that yes, on these ones we have an approximation of the current as this rooftop function, so a triangular type function, high amplitude in the center here, which we can see here, and 0 amplitude here at the edges. And then we know if we had some current here, we have some amplitude of these ones. So for example, amplitude I0 can be a complex number. the electric field everywhere can be written like this. And then we can sum up the contributions from all of those Hertzian dipoles and say that the sum of these has to be 0 at the metal, especially the tangential component. And that gives a linear system, a matrix that we can solve. And that is what's done inside of the computer in a slightly more refined way. So if we look at your half wavelength dipole, yeah, the total current can look like this. And what we do is that we say it's a sum of these small currents. So basically one coefficient there, one there, one there, and one there, and one there, and so on. So a lot of unknown currents, and we get a linear system that we invert to get the total current. And that is your meshing in these cases. In reality, you just put it up what the electric field is, and it can be written formally what we had, the equation before, can be written as an, let's call it green matrix, green dyadic, green tensor. It's a function here that multiplies the dipole moment of this little Hertzian dipole. You do it slightly more accurately actually in implementation. And then you use what's called translational invariance of this. The same thing that you've had in time domain for a linear system. You can write the electric field as a sum of these contributions. And if there are infinitely many, it becomes an integral. So this is the same thing as we had in, for example, a time, this Green's function is the same as the impulse response of a linear system. When you studied system theory, you send in a short pulse, you get the response. The Green's function is the same in space. And in space, you have 3 dimensions instead of 1 dimension. So we integrate this over 3 dimensions, over the entire volume. And if the current lives on the surface, we only integrate over the surface. And by doing this, we can combine it to this boundary condition. So we put that the electric field, the total electric field is 0 at the metal. And we divide the total field as an incident field and a scattered field. The incident field here is known. And then I should determine the scattered field. And the scattered field can be written up from, in these cases, my induced currents. That gives a scattered field. And that gives me actually my integral equation that I should solve. This is called the electric field integral equation. And it has only unknowns, which are these currents. And the discretization we do by expanding this in basis functions. And the rest is known because the green dyadic here is known. The incident field is known. I have one linear system and I can actually solve this. That's what's happening inside of FECO. And your meshing describes how accurately you're basically doing this. So you get many currents elements here, excitation to solve. You have these impedance matrix elements, which is this previous equation. You have some driven terms to the right, and you have a big matrix. You invert the matrix, and you have solved your problem. And the elements is just that's computed inside of the FECO, for example, and they compute these integrals here. This is almost the same as this Hertzian dipole I showed before, but you actually do this numerically. Everything in this equation is known because these are basis functions. You know what basis function you use. These are this Green's function that sits there. And again, here you take derivatives of the Green's function, you sum it up, and you get your impedance matrix. And then you invert these ones, and you have solved your problem. That is what's happening inside of FECO when you actually solve it. So I will not show you this Hallén's integral equation. That is the one that is used, inside of, no, not inside, but in the code, for example, of Orphanidis. They use a simplified equation for wires, which you can use in MATLAB and actually run some cases there. And it's a different type of equation, which is simpler to solve in these cases. But we will stop there for today. So at least some background of what's happening inside of this numerical solvers that you are using. So before we end, I know it's a very short overview of these computational tools, but you should have some idea what's happening there. Any questions about that? Okay, if there is no question, then before we end, we should bring up one thing, and that is, of course, that the lab starts this week. There is a questioning hour starting, I think, very soon. I don't know if it's in 1 hour or if it is now. It starts quite soon. And also for the lab, there are some lab groups which we believe have signed up for different labs. So what we've seen is, at least what we think is one lab group, have not signed up for the same hours. So check with your partner that you actually have signed up for the same hours to do the lab. And if you have not done that, send an email to Niklas, and then Niklas can take you away from the booking of the lab, so you can do the lab together with your lab partner, because you need to do it at the same time as your partner. You should do those together. So check that you have signed up for the lab, and actually that you have signed up together with your lab partner. And for the ones that have not done it, contact Niklas. He will remove one of you from the Euronymous lab, and then we can change. You can sign up for a new hours in a different one. But check that is really done. There is also a quiz open for the first lab, and it's some ideas there that you should just be prepared what comes at the lab, so you at least know those things that you have to know for the lab. And I know there was probably some errors in it, and if there are errors in the quiz, I move them from a different system. Just send me an email and I will fix it as soon as possible. There is also a new quiz opening up on Thursday, and if you have not done the 4th quiz, I think it is, make it before the first day lecture. Otherwise, I wish you good luck for the lab this week. I will close the recordings of this one.